Hello, welcome to Econometrics Melody. In this video, we will see some of the concepts related with Venn diagram, and this concept is also very helpful in understanding the concepts related with probability. Let us draw a Venn diagram where U represents the universal set, and we have two events A and B. They are not mutually exclusive because we have the common region represented by AB, and the region that does not belong to A union B, but it is the part of the universal set, is represented by A union B complement. It is quite obvious from the Venn diagram that the universal set constitutes of the region A union B, the entire region covered by AB, and then the region that does not belong to A union B, meaning thereby A union B complement. So cardinal number of U is equals to cardinal number of A union B plus cardinal number of A union B complement. Let us further expand this formula, and if we concentrate on the region covered by A or B, then we see that the intersection part AB or A intersection B is repeated in the region A and B. Therefore, the cardinal number of A union B is represented by cardinal number of A plus cardinal of B minus cardinal number of A intersection B. We exclude the repeated portion. That is, we subtract the cardinal number of A intersection B from cardinal number of A plus cardinal number of B in order to derive the cardinal number of A union B. Now, cardinal number of U, it represents the sample space. So let us divide both the sides by the cardinal number of U. Then we get the respective probabilities. Therefore, 1 is equals to probability of A plus probability of B minus probability of A intersection B plus probability of A in union B complement. The probability of A union B is equals to probability of A plus probability of B minus probability of A intersection B. And when added, the probability of A union B complement this is equals to the probability of the sample space, which is equals to 1. Therefore, the probability of A union B is equals to probability of A plus probability of B minus probability of A intersection B. It is due to this existence of the common region A intersection B that the events A and B are not mutually exclusive. A intersection B here allows for the occurrence of the events A and B at a same time, which is against the principle of mutually exclusive events. Mutually exclusive events are those events that cannot occur at the same time. If one event occurs, then the other event does not occur. So this formula is used when the two events are not mutually exclusive, that is, when they have the common region represented by A intersection B. And the counterpart when the events are mutually exclusive, so the set's counterpart for it is equals to the disjoint set, where probability of A union B is equals to probability of A plus probability of B, and the common region is 0. There is no common region in the disjoint set. The list of the events related with this Venn diagram are the events related with A or only A, and the events related with B or only B, events related with A intersection B, that is both A and B, and those events that are not related with either A or B, that is A union B complement. These events in the list represent the characteristic events for the process as indicated in the Venn diagram. Now let us see an example of two events which are not mutually exclusive events, and we'll utilize this formula. The probability of the sample space 1 is equals to the probability of A plus probability of B minus probability of A intersection B plus probability of A union B complement. Let us state the problem that 60% of the people have access to television, represented by event A, and event B represents that 50% of the people have access to newspaper, and 30% have access to both television and newspaper, represented by event A, B, or A intersection B. Now we need to find what is the percentage of the people who don't have access to either of the media. The total probability is 100%. And if we operate it, 100% is equals to 60 plus 50 minus 30. 60 plus 50 is 110 minus 30 is equals to 80. And therefore we have 80% plus probability of A union B complement is equals to 100%. Therefore probability of A union B complement is equals to 20%. Therefore 20% of the people don't have access to either of the media. The unique characteristic events related with this example is equals to either reading only newspaper or newspaper, either having access to only television or television, and either having none of them or either having both of them. Event A having access to television and event B having access to newspaper. These are not the mutually exclusive event because the person having access to both the television and newspaper refutes the principle of mutually exclusiveness. It is equivalent to occurring both the events A and B at the same time. A quick review of what we have seen so far. If cardinal number of A union B is equals to cardinal number of A plus cardinal number of B minus cardinal number of A intersection B, then in this case the events A and B are not mutually exclusive events because of the existence of the common region represented by A intersection B. But if A intersection B is equals to 0, then the events A and B are called as mutually exclusive events, and in that case cardinal number of A union B is equals to cardinal of A plus cardinal number of B. In set notation, set A and set B are called as disjoint set, and in probability, such events A and B are called as the mutually exclusive events. More precisely, for the mutually exclusive events A and B, probability of A union B is equals to probability of A plus probability of B. Through the above three relationships, we are clear about the notion of the mutually exclusiveness of any two events. Similarly, now let us talk about the independence of any two events. So if we are able to write probability of AB is equals to probability of A and B is equals to probability of A intersection B, if this is equal to probability of A into probability of B, that is the probability of A intersection B is the product of their individual probabilities, then we can say that the events A and B are independent events. In summary, the events are independent if the probability of their intersection is equals to the product of their individual probability. Now let us see a very useful law in sets called is the Demorgan's law. We can write A union B complement is A complement intersection B complement. And in a general form, we can say that the complement of the union of the events is equals to the intersection of their individual complements. Similarly, A intersection B complement is equals to A complement union B complement. So in general form, the complement of the intersection of the event is equals to the union of their individual complement. A complement is equals to anything but not A. So this is equals to universal set minus A, and in probability notation, probability of A complement should be equal to 1 minus probability of A. The shaded region in the Venn diagram represents A minus B, and we can also write it as A intersection B complement or simply AB complement. And the intersecting or common region is AB or A intersection B. And the region represented by B minus A is also called as only B or B intersection A complement or simply B A complement. Any region that do not belong to A or B but lie inside the universal set is called as A union B complement. Probability of B complement is equal to 1 minus probability of B. Similarly, probability of A minus B complement is equal to 1 minus probability of A minus B. Now let us see an example. A container contains 21 balls, identical balls, and 12 are white and 9 are red. If we select 7 balls, what is the probability of getting 4 white and 3 red balls? We know that there are 21 identical balls in total, and we need to select 7 balls to find the probability of getting 4 white and 3 red balls. We'll use the concept of combination in order to solve this, and let us begin. Probability of getting 4 white and 3 red ball is equals to, out of 12 white ball, how many ways can we select 4 white ball? into out of 9 red balls, how many ways can we select 3 red balls? So this is our favorable events, number of favorable events, and we divide it by out of 12 balls, in how many ways can we select 7 balls? So we are dividing by the total possible outcomes or events, and we know the formula ncr is equals to n factorial divided by n minus r factorial into r factorial. Therefore 12c4 is equals to 12 factorial divided by 4 factorial into 12 minus 4, 8 factorial, and 9c3 is equals to 9 factorial divided by 3 factorial into 9 minus 3, 6 factorial, divided by 21c7, which is equals to 21 factorial divided by 7 factorial into 21 minus 7 factorial, which is equals to 14 factorial. Now let us operate them and represent in a single numerator and denominator. This is equals to 12 factorial into 9 factorial into 7 factorial into 14 factorial, whole divided by 4 factorial, 8 factorial, 3 factorial, 6 factorial, 21 factorial. And this is for the equal to 0.3516, which is equals to 35.16%. So the probability of getting 4 white and 3 red balls when selecting 7 balls from the container of 21 balls containing 12 white ball and 9 red ball is equals to 35.16%. So this is it for this tutorial. Thank you very much for your time. Thank you very much. Econometrics Melody.